Assalamu alaikum, dear students. In my last lecture on probability theory, I spoke about moments about origin and moments about mean. In this video, I'll be talking about moment generating functions. Before jumping into moment generating function, I'll introduce what is generating function. The generating function is a function associated with a sequence. And the terms of sequence, they appear as coefficients of the terms of power series. We go one step ahead and we will talk about the exponential generating function. So if you for a while don't consider this term exponential, then the generating function of a sequence an is written like this: gan of x. So x is the variable used and an is the corresponds to the sequence. This is basically this power series, and a naught will be coefficient of, obviously a naught will be the constant term, a1 will be the coefficient of x, and then a2 will be the coefficient of x square, and so on. And when we will associate the term exponential generating function, over there we will make a change and we will divide this term by n factorial. And this is a separate debate that how this generating function and exponential generating function are related. I'll not be able to cover all that in this course, and I'll encourage you to just Google or look into some book of discrete mathematics to find out more details on the differences between generating function and exponential generating function. For the purpose of our class, this when we will be talking about the exponential generating function, I'll be talking about the exponential. Now I'll write the exponential generating function of a sequence an is, now let's say gan of x, and this is the terms of the sequence come over here, but now they will correspond, each term will be coefficient of such a term. So for example, for n equals to 0, I'll have x to the power 0 over 0 factorial, obviously again the same constant, but when when for n equals to 1, I'll have a1 and then x over 1 factorial, and again the term stays the same, but it will start changing from the second term onwards. So it will be a square x square over 2 factorial. So this is the difference. Now this 2 factorial is what is the difference between the generating function and the exponential generating function, and in our case we'll be using this exponential generating function. Okay, so I'll leave this a little different topic for you to study, and I'll be able to respond to questions only as far as this course is concerned. And if you need further details, then I can make a separate video on that. Okay, I come to this moment generating function of a random variable. So moment generating function of a random variable x, where it exists. Now why I say where it exists? Because I'll be involving the summation and the integral, and there is a chance that the summation doesn't converge, that that series doesn't converge, or the integral, the improper integral from minus infinity to plus infinity doesn't converge. So if it converges, that means where it exists is given by, so this moment generating function is the expectation of this random variable e to the power tx. And as you know, when we talk about expectation, we talk about this series e to the power tx f of x, and obviously this series means that x is discrete. The only difference from the definition of expectation is, now instead of x we have e to the power tx, and we'll try to understand what it is. And then for the continuous random variable, instead of the summation we will have the integral. Everything else stays the same. Conceptually, for discrete random variable we will have the summation, and for the continuous random variable we will have the integral. So in order to understand it a little more, I'll expand this e to the power tx, and then when I expand it, this is the Maclaurin series, this is 1 plus tx. If you consider the famous e to the power x, this becomes 1 plus x square over 2 factorial, and so on. So if I consider e to the power tx, this becomes 1 plus tx plus t square x square over 2 factorial t cube over 3 t cube x cube over 3 factorial and so on, tr over r factorial x to the power r, and it goes on. And now when I consider mx of t, so instead of e to the power tx, I replace this e to the power tx by its Maclaurin series, and over here I have f of x. So when I multiply this f of x term wise and I open this summation, what I obtain? The first term becomes simply the sum of f of x, which is the sum of probabilities, and this is 1. The second term becomes t x f of x, and then this summation. So I take this t out, and this is x f of x. This is nothing but the expectation, and or you can call it the first moment about origin, or you can call it mean. So this is e to the ex, and then for the second term, when we do it, so this is t square over 2 factorial x square f of x, and then this summation. So this is the second moment about origin, and this is what I have written. So this is 1 plus t at e to the power x, t square over 2 factorial e x square. This is the second moment, it goes on, and then it becomes 1 plus mu of t, and then mu 2 dash t square over 2 factorial, and then mu 3 dash t cube over 3 factorial, and so on. And now you can see that this mu, this is coefficient of t, this mu 2 dash, this is coefficient of t square over 2 factorial, mu 3 dash, this is coefficient of t cube over 3 factorial, and so on. So this is something very close to that exponential generating function. And now the coefficients, these are the moments. And just to get going, if we consider a random variable with this probability density function, f of x is e to the power minus x for x greater than 0, and this is 0 elsewhere. So if I am interested in its moment generating function, then this becomes e to the power expectation of e to the power tx, and this is from 0 to infinity e to the power tx, and then instead of f of x I put e to the power minus x, and this after this is something very routine. This becomes e to the power x times 1 minus t, and mind you, this is an improper integral. So if this is an improper integral, when we will be substituting those limits, we'll have to keep an eye on for what values it converges and for what values it diverges. So please note that if t is less than 1, that means this is 1 minus t is less than 0. So that means this whole thing is negative. This negative multiplied by this negative will stay positive, and this will play a role. And when you integrate it, you make those computations, you will be seeing that everything is fine for t less than equal to t is less than 1, and when t is greater than or equal to 1, this integral does not converge. So that is again a routine computation. And this integral, when we integrate it and put these values, this is 1 over 1 minus t, and this is true for those values of t which are less than 1. And now this 1 over t, you know that this 1 over t is equal to this series, and you sometimes call it the binomial series. Other times you give it different names. So this becomes 1 plus t square, and so on tr. And in order to figure out our moments, we do what? We multiply, for example, 2 factorial over here, 2 factorial over here, 3 factorial over here, 3 factorial over here, and so on, r factorial over here, r factorial over here, and this goes on. So that means if I am interested in my first moment, that is 1. I am interested in second moment, that's 2 factorial. I am interested in third moment, that's 3 factorial. I am interested in rth moment, that is r factorial. And now by looking at this series, by looking at this value of mx of t, if we consider rth derivative of this mx of t and we put t equals to 0, we obtain those moments. Now please note that when mxt is equal to 1 plus mu t plus mu 2 dash t square over 2 factorial, and so on, when I consider the first derivative, this term becomes 0. This term becomes mu, and t becomes 1. And over here I will have a term involving t, and over here I will have a term involving t. So when I put value of t equal to 0, so all this term and the remainder term, they will all vanish because t is 0. and I'll be left with what? Simply mu. If I take two derivatives, both these terms will vanish, and this term will have only constant, and all these terms will be involving t. And when t equal to 0, all these terms will vanish. So we have a very straightforward theorem, and that if you take rth derivative of this mx of t and you put t equals to 0, we obtain the rth moment about origin. And then we note very simple properties of this moment generating function. So if, for example, this is only for staying updated for what is to follow. So this, if we have m and instead of x we have x plus a, we obtain what? We obtain, instead of x we put x plus a, so this is expectation of e to the power x plus a times t. And if I separate this out, this becomes e to the power tx, and then this e to the power at, and this e to the power at has no involvement of x, so it may go out like a constant, and this is, we are left with e to the power etx, and this is nothing but the mxt. So from here we can see that this mx plus a of t becomes eat, the old moment generating function, mxt. Likewise, if we have mbx of t, so this is expectation of what? etbx, and now if I write this, I can write it this mx, and instead of t now I have d of t. So this again we are making little modifications with the random variable. Over here we added, we scaled it, over here we multiplied it by a scalar, and now please look over here. Now we have x plus a divided by d of t, and this is expectation of e to the power t x plus a over b, and then this becomes e to the power t a over b, and then we are left with expectation of e t x over b, and this becomes e a over b 3, and then whatever is left we write it like this. This is m of x t over b. So these simple identities we prove them for our later use, and nothing difficult in this. So you will go through all this material, and I'll encourage you to understand the concept of generating function and exponential generating function, and then the rest is something very simpler. We are using only the properties of expectation and Maclaurin series, and all these topics, all these little concepts, they make the content of this lecture. Thank you very much.